Thank you all for joining today's webinar. My name is James Truckle and I'm an applications engineer at Plexim. I'm joined today by another applications engineer, real-time simulation engineer, Brian Lieblick, and a Plexim developer, Dr. Beat Arnett. Both of them will be participating later in the webinar. And we really have a unique topic today, and I'm excited to be introducing our agenda and providing a foundation for what we're going to discuss with focus on the latest code generation capabilities offered by Plexim. So we'll start with just a quick introduction to Plexim and the simulation software PLECS. I'll then introduce the PLECS Coder, and then Brian will show us his test setup and start showing control models that integrate the Texas Instrument target support blocks. Along the way, we will hear from Dr. Arnett, who was a senior developer of the PLECS Coder. Feel free to ask any questions and we will do our best to answer. You can ask questions at any time during the webinar using the GoToWebinar control window, and they will be answered when appropriate. So here's just a very quick introduction for those who might be somewhat unfamiliar with our company. Plexim creates design tools for the development and testing of power electronic systems. We've been around since the late 90s, early 2000s, and are headquartered in Zurich, Switzerland. The company was founded actually and spun off from ETH Zurich in Switzerland. It's still privately held. We have two additional facilities, one in Cambridge, Massachusetts, and one in Seattle, Washington. The tools that Plexim offers are, you could call them a simulation platform, and really this encompasses quite a few tools. First and foremost, the PLECS simulation software, which I'll describe briefly. There's two versions of the tool, one fully integrated into MATLAB Simulink and one as a standalone independent tool. We have additional tools that facilitate the testing and validation of embedded control software. These would be PLECS processor in the loop, as well as a real-time simulator called the RT-Box that facilitates and enables hardware in the loop testing of control platforms. And now we also do have this additional capability of generating code using the PLECS Coder. PLECS is widely used in both academia and industry for developing power electronics products. Using PLECS, you can, as I said, model a complete power conversion system. You can get robust and fast simulation results either within the MATLAB Simulink environment or in a standalone tool. And the component libraries are very comprehensive. They cover not only the electrical, but also the magnetic, mechanical, and thermal aspects of power conversion systems. And of course, their associated controls can also be modeled in the tool. So using PLECS, an engineer can quite quickly model a complete wind turbine system, perhaps, or a solar inverter, or a motor drive, or a power distribution system, or a power supply, for example. Once the plant system has been modeled using these physical domains, we can start to talk about control system development and modeling in PLECS. And PLECS does support the realization of any analog or digital control scheme. Sophisticated and realistic algorithms can be implemented using continuous or discrete digital signal processing blocks. The library is very intuitive. It's easy to learn. If you've traditionally used other tools for control development, the transition to modeling and developing controls in PLECS should be quite natural. Here we can see just very quickly in this schematic that the control blocks are connected using green signals as seen in the model. and we'd be populating the schematic with components from the library browser, dragging and dropping, connecting them together with wires. So the tool is very intuitive and easy to learn. If you do want to come a little bit closer, perhaps, to a hardware implementation of a control system, there are additional blocks within PLECS to implement so-called software-in-the-loop simulations. And this is a powerful capability, and it allows you to implement the model of real power electronics hardware and software in a simulation environment. So you can directly add C code into the simulation using a built-in C script block within the library. You can also use a DLL block where you can compile an existing algorithm into a DLL, which can then be added into the simulation with a fixed step size. So further validation and testing can also be done using Plexim's tools. We offer, as I mentioned, in-the-loop solutions such as hardware-in-the-loop or HIL, or processor-in-the-loop, otherwise known as PIL. So these two offerings do offer capability allowing you to validate the control system. So introducing the PLECS Coder here, once your control strategies have been sufficiently developed and tested offline in PLECS, a common next step will be then to write a target-specific software that runs on a DSP or an MCU, for example. When used within PLECS's workflow, code generation can reduce coding time and debugging. Additionally, it can allow rapid iteration on control and design. And as we'll soon see in some of these demonstrations, the models we develop in PLECS can run offline first in the simulation environment offline, and then the same model can be used to write software to run on embedded processors in real time. Great, so with this workflow in mind, PLECS, processor in the loop, code generation, and the RT box, there's really a variety of development approaches and paths that can be taken. Today, we're going to look at what we call a power code gen workflow, where we're going to generate embedded control software for a microcontroller, and we'll test that control software with an actual power stage. But using the other tools and the other paths, you can see, and we'll discuss how controls can be developed as a workflow. So for those that don't know, the PLECS Coder is not necessarily a new tool for Plexim. It's been around for several years. Up until this point, our users have been able to use the tool to generate C code to execute plant and control models on our real-time simulator, the PLECS RT box. It's also been possible to generate generic C code to be then massaged for execution on specific processors. The approach that we've taken to generating code really allows us flexibility and it facilitates adding additional targets. So what we've done is we've most recently added a target support package for the Texas Instruments C2000 families, where we can take generic C code, add a wrapper layer that references underlying hardware drivers, and then create a component in PLECS with rules on how to generate the code. So before I hand it over to Brian to get started in PLECS and introducing his test setup, these are the requirements for this code generation workflow. We do need a license of PLECS 4.3 or newer. The PLECS Coder is a separate license, and then the target support package can be downloaded for free from plexim.com. All of the required packages and download links are on the website. You can also request free trials of this software if you'd like to do so. And with that, I will transfer the presentation over to Brian.
Great, thanks, James. So today I'll show two demos, and they'll both use the PLECS TI C2000 code generation tool. And my goal for these demos is to highlight that the code generation tool is very easy to use, and it's powerful enough for real control applications. It's also flexible enough for expert users experienced with embedded programming and digital control. It has something to offer them as well. So the first demo that I'll show is going to be a very simple one where we'll use the coder to generate PWM signals and spin a motor in open loop. We'll build this model up from scratch and discuss key components and focus largely on the code generation workflow. The second demo is going to expand on the first, where we'll deploy a pre-built controller using field-oriented control, or FOC, and we'll show it can be used to test different control implementations and dive a bit more into the timing of the embedded control loop, which is one of our coder's unique features. We'll also view data from the code executing on the microcontroller and change some set points in real time. So these demos are focused largely on motor control, but you should see that these concepts can be applied to any number of different power electronics applications. So both of these demos use a common hardware setup that I won't explain in a little bit more detail. So the main components in this setup are shown on the slide, and also just let me share my webcam with you so you can see the setup on my desk as well. So starting from the microprocessor, we have a TI 28069 launchpad, and there's a USB cable that connects to my PC, which we'll use to program the microcontroller directly from PLECS. We'll also use this USB cable to connect to the microprocessor via a serial connection to receive real-time waveforms and manipulate some set points in the control code on the embedded target. So when PLECS is communicating with the control logic executing on the microprocessor, I'll refer to that as using the external mode, which means that the PLECS schematic is synchronized with an external source. In this case, it's going to be the launchpad device. So next is a three-phase GaN inverter made by TI, and that receives the PWM signals from our launchpad, and it also provides integrated voltage and current sensing. So the voltage and current sensing outputs from the inverter connect to the ADC pins of our launchpad. The inverter is connected to a 24-volt DC supply, as well as the motor phase connections. So the motor that we're controlling today is a 24-volt brushless DC motor with integrated Hall sensors, as well as a quadrature encoder or QEP. And we'll use both the Hall sensor and the QEP in our closed loop control example. These motors are sitting in a 3D printed test fixture, and so we can send you the design files for this if you're interested. There's also a second motor in the test fixture that's not controlled or connected, and in this case, it acts as just a bit of extra inertia and load on the shaft. This slide shows the signal flow here, just in a bit more detail. So you have the PWM modulator connected from the launchpad, connected to the booster pack. And then the booster pack, you have voltage and sensing signals that feed back into the ADC pins of the launchpad. The terminal connections also of the inverter are connected to the motor here, and then the Hall and QEP sensors are connected to the QEP input and digital inputs on our launchpad device. And then this slide just shows the booster pack circuit in a bit more detail, and we can see that it comprises of 3 GaN half bridges here that are a 3-phase inverter, and they connect to PWM signals from our launchpad via this buffer circuit here. There's a sense resistor located in series with the output to the motor terminal connections, and then there's an amplifier circuit that then feeds that to the ADC pins of our controller. And so with that kind of orientation of just how things are set up, let's go to PLECS and start generating code. So with that, I'm going to close that. And I just want to share the library that we have here on the left-hand side. So they're all the traditional PLECS control, electrical, thermal libraries. And then when you receive the C2000 target, you actually get a set of library components along with that. So you have everything that you kind of would need to configure these microprocessor peripherals. So we have ADCs, digital I/O, PWM generation options, as well as certain other components for timing and synchronization effects. So let's open a new schematic here. And since we know we're going to be generating PWM signals, let's drag and drop this PWM component from our library. And we're going to use a sine wave generator here to generate the modulation index for our PWM controller. And while we're at it, let's also add a scope and connect that to the output of the sine wave generator. Okay, and so let's look at the settings for this PWM block here quickly. So we can see in this case, we're going to use 3 PWM generators to generate a signal for each leg of our half bridge. And so we're going to use PWM generators 1 through 3 in this case. And each one of these PWM outputs is a complementary PWM pair. And so we're going to generate signals for the upper and lower switch in each one of those half bridges. We also notice here in this description that the carrier is between 0 and 1. And so we're gonna want that duty cycle input to be centered somewhere around 0.5. So we're gonna have this symmetrical carrier, and we'll keep it at 20 kilohertz. And there's a few other settings here that, for example, enforce certain timing restrictions and set up the dead time or blanking time between the switching for this complementary PWM pair, as well as a polarity option. So there's also a few other tabs here that can set up certain triggering options and protection settings for our PWM output that we can configure if needed. But one thing you'll notice here is that everything that we're entering is similar to a typical PLECS PWM block. There's no specific register configurations. Everything is handled by the code generation tool. And so with that, our PWM is configured. And so let's go set up our sine wave quickly. And so we're going to want to have a 0.2 amplitude sine wave. And let's have this biased around that 0.5 point I mentioned earlier. And we'll generate a sine wave at 20 hertz and make this a balanced three-phase output. And so we'll do 0, minus 120, and 120-degree phase separation. So now we can run this model quickly and see that we're getting our sine wave output as expected. And we can also save it. So we'll just save, and we'll save this on my desktop as open loop. There we go. And also, there's one other detail that we need to include, which is the enable signal that goes from our controller to the GAN inverter. And so we're just going to set another digital output here. That's GPIO 50. And we're going to connect that to a constant signal to enable or disable our output. And so we'll just set that value to 0, and we'll call this constant EN. And so with that, that's the basic schematic of what we're going to be running today. And so next, let's just start to generate code. So all of the code generation interface happens from this coder options dropdown. You do need a PLECS Coder license to be able to see this. So here are the general settings. So this just specifies some of the discretization options and how our control loop executes a little bit. So this basic setting here, it not only specifies the discretization step size in terms of how our continuous state space model is discretized, but also specifies how often our control loop interrupt is triggered. And so in this case, we're going to set it to 20 kilohertz, which is the same frequency as our PWM generator. So the next tab is the parameter inlining tab. And here, when we generate code, we can hard code certain parameters in the code for certain code size and efficiency purposes. And then we can also specify some exceptions to that default behavior. So example, if we want to keep certain parameters tunable. And so this window, by dragging and dropping this enable signal into this window here, it just specifies that we're going to want to tune this and turn this on and off during our simulation in the code running on our processor. Now the last tab here is this target tab, and so we can generate code for generic C code that can run on our desktop. We can generate code for the RT box, and then these are the processors that we support today. So we're going to generate code for the 28069, and there's a few settings here, for example, clock frequency, and again, some timing restrictions. And then in this build options, we have two options. We can build and program from PLECS, or we can generate code into a Code Composer Studio project, or CCS. And CCS is the IDE for TI embedded processor development. So we supply a pre-configured template as part of the support package if you want to generate code using that option. And the big advantage of that is that you can use embedded debugging tools included in Code Composer Studio. So let's set build and program. And then the last thing that we need is the target configuration file for a microprocessor. So the target configuration file just specifies the communication settings with our target, and you can generate that from Code Composer Studio or from TI Uniflash. And so with that, I think we're ready to generate code. And so if we just click this build option here, we're going to compile. And while this is happening, you'll actually notice on my desktop that there's this new open loop code gen folder. And if I double click that, we can see that we have this openloop.c. And in here, we can actually inspect the generated code. And we'll just zoom in a little bit. And we can look and see, for example, here's this initialization code, and we can actually read what exactly our generated code is doing. So we're setting up in this initialization step our PWM output. And for those users experienced with the C2000 targets, you can see here setting up our action qualifier, our up-down count mode, and a few other settings here. So it's all readable and it's all inspectable. And you can also look at the rules by which we generate this code. So it's all open from top to bottom, and you can see exactly how it's working. So with that, the code is deployed now onto my target, and we can actually see that we're spinning this motor. So it's just that easy to start generating some PWM signals with the target support package. We can also now connect to the external mode. And so this is that tool where we basically start streaming data from a buffer on the embedded processor into our PLECS Scope. And so if we just connect to it via serial connection and hit OK, and connect and hit activate auto triggering, we're going to start seeing information from this scope updating in real time. So we'll just change the decimation to get a bit more data in this window. And we can see here that we're updating this value with the data from the sine wave generated on the microprocessor. And so if we want to add some more functionality to this basic model, one thing we can do is we can just drag and drop an ADC component onto here. And so let's add a plot above, and we'll just drag this down low and connect the ADC to our scope. And we're gonna configure this ADC setup. So again, this setup here is all kind of intuitive. You have an ADC unit. You can select which ADC inputs you're gonna use, as well as certain scaling and offset parameters. And so we're gonna use analog input channels 0, 8, and 1, which correspond to the current sensing and the GAN booster pack. And we'll hit apply, and we'll just hit build again. So we're gonna go into this coder window, target, build, and we should see that if we look at our open loop code, we'll see that we have generated a new set of code just now at 4:22, and we're building, we're flashing, and momentarily we should see that the flashing process is complete and our motor will start spinning, and then we can connect via the external mode and see that data in real time. So we just wrapped up the motor spinning, and if we click connect, activate auto triggering, now not only in the scope are we seeing the data from our PWM output, but we're also seeing the currents that are flowing in the motor here. And this is actually the voltage applied to the ADC pin. So it's representing that value from 0 to 3.3 volts. So again, the highlights here are just that we're able to get this motor up and spinning really quickly, start reading current measurements, and just see that the code generation interface here is very streamlined. So you don't get bogged down in some of the technical details and see how things are working, but everything is still at the same time very open and inspectable.
Great, thank you, Brian. I'd like to pose a question to Dr. Arnett at this time. Keeping in mind that our users do have varying degrees of understanding of the TI C2000 MCUs, what were the main objectives and motivations for the development team when starting work on this target support package?
Sure, and thanks for giving me the opportunity to participate in this webcast. Our main motivation for developing the C2000 TSP really is to make embedded controls more accessible to engineers and students, especially those who have very limited or no experience with microprocessors. The unfortunate fact with microprocessors and their associated development environments is that they can be quite intimidating. I don't know, James, have you recently looked at a microprocessor datasheet?
Yes, I was quite intimidated.
Yeah, that makes sense, right? So you probably noticed that there can be thousands of pages of material. In fact, the latest technical reference of the TI C2000 processor is over 5,000 pages thick. So getting up the learning curve on a particular MCU takes quite a bit of time, and one has to study and understand literally hundreds of low-level configuration registers before even being able to generate or execute a simple control as Brian just demonstrated it. So our TSP essentially replaces low-level bit-based register configurations with intuitive physical parameter settings. So Brian, if you could open up the PWM block again, let's just take another look here at the parameter settings. You will notice that the parameters really speak to what we want from them. So we're not setting bits in weirdly named registers or thinking in terms of timers and counters, but instead we're directly punching in a switching frequency, a carrier waveform, and dead time. So that makes the microprocessor much more accessible. And the other blocks in our component library have been developed in the very same spirit. Another objective of ours was to make the C2000 target support package particularly useful to power electronics engineers, which is really the user base of PLECS. Most power converters these days are based on some sorts of digital controls that makes them more configurable and allows implementing more sophisticated algorithms compared to purely hardware-based solutions. So we therefore really made sure that our components in the library and our demo models as well are well suited to get power electronics engineers jump-started with implementing their own digital control algorithms on microprocessors. Back to you, James.
Great, thank you, Dr. Arnett. As a follow-up, for someone that does have experience with TI C2000s, is this still an appealing solution for them?
I would say so. Using a model-based approach has many advantages. For example, it can simplify the review of control algorithms with peers that may not be that fluent in programming languages. So looking at a PLECS schematic makes it more intuitive or makes it easier to understand what's going on than looking at a bunch of lines of C code. Also, by generating code from a simulation tool such as PLECS, you can then visualize what's going on in the real system within the simulation tool. So the waveforms that are showing of currents and duty cycles in this first example, they can then be compared against offline simulation or post-processed quite easily to confirm the correct functioning of your models. And along the same lines, in terms of verification, and validation of your control algorithms, if you're using a model-based code development environment, you then have access to other tools such as software in the loop, processor in the loop, hardware in the loop, concepts that you quickly introduced, James, at the beginning of the presentation.
Sure, great, thank you. I'd like to drill down a little bit into this concept of power electronics engineers and the specific requirements that embedded controls engineers working on power electronics applications have. Brian mentioned that the PWM block included settings to configure triggered events. In power electronics, we know that sampling and the timing of these events are very important. Can you expand on how the interaction of triggers are represented?
Sure. Yes, you're making a very good point there, James. The timing and the synchronization of events in power electronics systems is hugely critical. Often switching frequencies are high, time constants are relatively small. So it is important that measurements are taken at the right time and that the PWM duty cycles are updated in a synchronized fashion. So what we have introduced with the latest version of PLECS and the first release of our target support package is a new domain that we call the trigger domain, and Brian will demonstrate this to you in his next demo. It's sort of a reddish color that allows you to specify the synchronization of the different components, different peripherals of your microprocessor in a graphical manner. So it makes it very intuitive when you look at the model to see how the synchronization happens. But also, even more importantly, those synchronization signals actually function during an offline simulation. So what that means is if you are running an offline simulation first before you're deploying your code onto the microprocessor, you will get identical timing behavior as you will get when it's deployed onto the chip.
Okay, well, with that, I think we all want to see the next demo. Brian is going to show a little bit more of a detailed model here, so I'll hand it back over.
Great, thanks James, and thanks Dr. Arnett. So the next demo we're going to look at is a closed loop demo of a field-oriented control, or FOC. And so for those of you who aren't familiar with FOC, it's a widely deployed motor control technique that's quite attractive for many different applications, and it involves controlling the orientation of the motor's stator current space vector to be at 90 degrees with regards to the rotor flux axis. in order to achieve the maximum torque per amp. So a crucial piece of information for field-oriented control is the angle of the rotor flux, which we were able to get in sensored applications from the counter value of our encoder mounted on the motor shaft. So with that, let's transition back into PLECS and look at this demo. And so if we go to the demo here, we have a quick overview of the system that we'll be controlling today. And so this should look familiar. This is just a representation of the hardware I showed earlier. So here we have this motor. Here are the stator phase connections. And then this purple connection here is the motor shaft modeled in the mechanical domain. And so here we're connected to that little bit of extra inertia, which is the second motor on that shaft, as well as the friction that's included in this system. We also have our 2-level GAN inverter, and we have an enable signal coming from our power stage as well as the PBM signals that then modulate the switches in this simulation. We're also measuring the 3-phase current. So here we have this IS measurement, as well as the DC voltage here, VDC. And then on the left-hand side, we have these measurements fed back, and there are a few subsystems here that also represent physical equipment in this hardware setup. So here we have this IS and VDC being sent basically into a block that linearly scales those measurements to represent those sensing circuits that I showed you earlier. And so the value here, ADC prime, actually models the voltage that would be applied to the ADC pin given an amount of current or sensed DC voltage. So there's also 2 other models here, and they model the QEP and the Hall sensors. And so they take the speed and position of our motor, and then they translate that into a digital pulse train for the QEP, as well as digital signals for the Hall sensor. So briefly, Hall sensors rely on the magnetic field of the rotor to detect the rotor position. So typically there are 3 Hall sensors arranged around the motor, which result in a position accuracy window of 60 electrical degrees. A quadrature encoder has finer resolution on the rotor position, but an index pulse is required that is needed to detect the absolute position. And that index pulse is triggered only once per mechanical revolution. And so before that pulse is triggered, for example, during startup conditions, then the Hall sensors provide more accurate position information. So once that index pulse is received, then the QEP has better resolution for the rotor position. So this subsystem here represents the control logic that we want to deploy onto our C2000 target, and we're going to be generating code for everything contained within the system. So let's look at it in a bit more detail. So here we have some rectangular components around the periphery, and these represent components from our target support package. And so these are the things that we want to generate code for. So we want to configure the ADCs as well as the QEP and PWM output and so forth. And so what you can see here is that we have this ADC signal, and it is configured similarly to what we had before. And so there's scaling and offset parameters, and we're measuring those 3-phase current measurements that come in, and then we have that sent here. And this here is just a little bit of logic that nulls the current measurement before we receive this enable signal. And coming out of here is this current measurements that are transformed into the DQ, or rotating reference frame, by this angle theta. And this uses our QEP sensor and Hall sensor. And what it is once that index pulse comes high, we transition between using the Hall sensor to determine our angle theta to using our QEP to determine that angle theta. And so you'll see that transition in the simulation. So coming out of here, we have our DQ current measurements that we're going to try and regulate to. And then here are DQ current set points. And next up, we have our current regulator. And if we were to just look at this in a bit more detail, so if we go subsystem, look under mask, we can see that we have our independent D and Q PI regulators. And if we were just to look underneath this one more time, we see here that we have this implemented in the digital control domain. So using unit delay and 0 order holds. We could just as well have this implemented in continuous domain. And then when we generate code, we automatically discretize that based upon that discretization setting I showed you earlier. Alternatively, we can configure this as a configurable subsystem, and we can evaluate different control topologies. So for example, here, this is again another PI regulator, but if we look under the mask here, we actually implemented this in C code. And so if that's kind of a more native way for you to write some control code, but you don't want to spend too much time setting up each ADC and PWM register, this might be an attractive option. And it can still integrate handwritten code into the generated code using this approach. So then coming out of here, we have our correction voltages, and then we generate PWM signals based upon that. So one thing you'll notice here is that dashed reddish domain that Bayat mentioned earlier. And so coming out of the PBM block here, we notice this ADC trigger, and this is the triggering domain. So this ADC component connects to the ADC trigger shown here, and then coming out of that ADC is a task. And so the sequence of events is that we actually have this PWM in this events tab. We're saying we want to generate that ADC trigger aligned with the overflow events of our PWM counter. And I'm going to show you an example of that visually in a minute. So once we have that ADC trigger come in, then we're going to trigger our ADC channels, and each channel takes a minimum of 75 nanoseconds on this processor to convert. And then once we have the latest measurement data from all of our analog measurements, we're going to trigger the control task. And so that will execute the main control loop and this PI regulator and all of that shown on the screen. So just to visualize this a little bit more, we can go to the slide that shows that in this case, we're going to be switching at 20 kilohertz. And then we have our control task running at half of that frequency or at 10 kilohertz. So here we see our switching period and our control period. And then aligned with that overflow event of our modulator, of our carrier. So we see this carrier going from 0 to 1 or underflow to overflow. And at these overflow events, you'll see that we're going to generate that ADC trigger. There's going to be some small latency as those ADC channels are converted, and then we'll run our control task. And then finally, once our control task has completed computation, then we're going to load that value into the output of the EPWM module via this shadow register technique. And that's getting into the details a little bit. And as Beat mentioned, we also have the option here of modeling that offline. So all of that is modeled explicitly here offline. So when we actually are running the simulation, there's a pulse traveling along this trigger domain that then actually triggers these ADCs and then the control task. And if we were to actually look underneath this mask and see how it's implemented, we can see that aligned with our modulator, we're actually generating these pulses in simulation. These pulses then come out, and then we have underneath the ADC, if we look at this, we'll see that we have a behavioral model here of the ADC. So that value is sampled and hold. We have the option to model some quantization, and then the scaling, offset, as well as delays associated with the process are all included in very good detail in the model. And so with that, I think let's run the simulation and we can see the results. And so again, this whole simulation here is functional offline. So we can look at measurements at this level. We can also look at measurements here from our current controller and from our position sensing logic. And so here we're going to look at the phase current going into the motor. So this is the ABC current, and then we have the current in the rotating reference frame, or DQ. And we can see here that we're starting up using that QEP sensor. And so we have this kind of blocky current control. And you can see this current pulsation that happens about 3 times. And that's every time that Hall sensor changes, we kind of are off in our angle measurement, and this leads to a current transient, which in turn will lead to a torque transient that you'll feel in the motor output. But then once we receive that first QEP index input, which happens right around here, right around 0.6 seconds, we can see the QEP angle reset, and then the Hall sensor and QEP output align. And at that time, we start getting these nice sinusoidal currents that we're generating. And so with that, we can save these traces as offline. And what we're going to do later is we're going to benchmark these offline traces against the code running on our microprocessor. And so the process, again, is very similar. We just go into this coder options tab, and we click build. And the settings here are the discretization step size. We have some parameters inline, so we're going to want to be able to change our current settings as well as an enable signal. And we're going to generate code for this 28069 processor. So we'll click build. And while it's happening, we also have the option to look at some other things in more detail. So we can look, for example, how our current regulator is performing. And so we can see here that our FOC is operating as expected, where this green here represents our stator current space vector. And then this red line represents the rotor position, and they're nicely at 90 degrees at the end of our simulation. So our simulation just finished generating code, and it should be deployed to the microprocessor. And so what we can do is we can connect again to the external mode here, and again turn our schematic into a interactive scope that says what's happening on the microprocessor and what signals the microprocessor are sensing. So let's go back into our controller, and if we just toggle this signal here, we'll see that our motor is actually spinning right now. And so we're controlling that current output in real time. You should see this value updating to about 2 amps. And so we're regulating the current to that desired set point. What we can also do is inspect these signals in the scope, and I can just go into this coder options and do a bit better job of aligning this trigger here. I can actually just do it directly from the scope. And so if I were to just try and align these two signals a little bit better, we can see that we have a really nice overlay of the measured and sensed current. I think the magic value here is going to be 3.1. So with a bit of effort, we can align these, but we can see that we're generating some nice sinusoidal waveforms that here align fairly well with the current measurements that we ran in this offline simulation. So we can see again, we're regulating this current output in real time to our target value of 2 amps, and we're seeing very little D-axis current. So we're achieving our regulation goals. And then we can start to manipulate some things in our schematic. So for example, if we change this current set point to 4 amps instead of 3, we'll notice here that our motor is spinning faster. And I'm just going to turn this offline trace. We can see that the frequency output in our sense current is increasing, as well as our output angle is showing that our motor is spinning faster as well. And then we can also do some other manipulation. So if we want to say spin this maybe in the other direction, we can also do that as well. So if I just change this to -2, we'll see now that we changed direction of our motor. And so with that, it just, again, highlights that we're able to create a practical closed loop control system here using these blocks in the PLECS code generation tool, as well as some blocks from the PLECS library. And we integrated all of these sensors. So we have the ADC, the PBM, the QEP, digital inputs, and we're all able to integrate that into a practical closed loop application. And then we also talked a little bit about just how these timing events are modeled, both in simulation and then also in the actual code that we generate.
Okay, thank you, Brian. I'd like to ask Dr. Arnett another question. Can you say something about code certifications and how the coder workflow enables engineers to ensure that control software is fully tested and validated prior to deployment?
Absolutely, excellent question. Using model-based development tools is a critical ingredient to passing a safety certification. And PLECS, pretty much from its inception, has always supported sort of a top-down development approach where you start out with a simple model and then refine it over time. And all along the development process, you test and validate your implementation. So that you can go into the certification testing with a lot of confidence that everything has been appropriately tested and validated. So what the coder does essentially is it extends this workflow from a very crude offline simulation to a product that is actually doing something real, controlling a real plant. So with PLECS, we have a very linear workflow, a very continuous workflow from that offline model where you might do some offline simulations, maybe verify your controls in a scripted fashion, automated fashion, potentially running some Monte Carlo analysis all within simulation, and then you start moving towards generating your control code. And the first step there, before you even go into the real hardware, might be to generate code and run it within PLECS. So you're still working with offline simulation, but now you're validating and verifying the generated code. After that, you may move to processor in the loop and execute the generated code on the actual microprocessor, but still within a PLECS simulation environment. So there again, you can test and validate your implementation. You might then move to driving a simulated plant using a hardware in the loop platform. That's also supported quite nicely with PLECS, especially in the conjunction with the RT box. And then finally, when you've gone through all these steps of testing and validation, refining your implementation, you can then deploy your code onto the real system. And what you may also want to do is inspect the code that PLECS has generated, which is, as Brian pointed out, quite human readable and could be another step towards assuring that the quality of the code and eventually getting your certification. Does that answer your question?
Yeah, that's perfect. So we've had a couple of questions come in from the audience. Someone noticed that in our target support package, we didn't include the legacy TI MCU, the TI 28335 Delfino. Is this something that we plan on supporting in the future?
The good old 28335, yes, which is about 15 years old probably at this point and still widely used in industry. Yes, we're gonna ask support for this chip in the next upcoming release of the target support package.
Perfect. If you do have any other questions, now's the time to ask them. A question we've received before has been about phase shifted PWMs, and I think anyone can answer this, but actually within PLECS, within the target support package, there is a special block called the variable PWM block, which will support generated code for phase shifted PWMs.
And just to add on to that, James, we also have the option to synchronize those PWMs with, say, each other, as well as synchronize them with an external source. And so there's a lot of flexibility here in terms of how we actually use that, for example, in terms of like phase shifted buck boost converters and so on. So it is useful for those applications.
Okay, with that, we do now conclude the webinar. A follow-up email will be sent that includes a recording, a link to watch the recording. The slides can be available if you send us an email separately. Our emails are included in this. You can find our emails through the control panel. You can also email info@plexim.com with any support questions at any time. We're more than willing to do personalized demonstrations and presentations for your colleagues, your fellow students, and your professors. So please reach out to us if there's any additional information that we can provide. And just a reminder that all of this is available to try for free by requesting free trials on the web. So thank you very much for joining, and we hope to see you next time.